Hello, this is June. Continuing to read Concrete Mathematics by three infamous mathematicians and computer scientists. We're to continue on the Josephus problem. Here we have discover generalized case on how Josephus problems work, and we're gonna generalize more and more depending on what constants we use. But before I get into that, there's another great discoveries made in this textbook that the Josephus function turns out to have really good patterns. I mean, not good, but amazing patterns to show us, and that is if we represent n by binary representation, that number of ones become the power of 2 and then subtract and then minus, and you do -1, then that's the result of the function. So say Jn, for n to be 2 to the power of m and all the way down to 1, the coefficients you see, it's either going to be 1 or 0, and you can really express it with in binary, just writing down the coefficients, right? The coefficients is basically whatever you have 1, you count them 1, 2, 3, 4, 5, 6, 7 in this case, then the answers to Josephus problem is going to be 2 to the power of 7 minus 1 is going to be your answer. I don't know how it is discovered. It's very, as the text mentions, curious but true. Well, we're going to get into how we can prove this solution, but it's definitely something we can explore more as we go through the textbook and continue to read. Let's continue to read what it has to say for us. So let's return briefly to our first guess that Jn equal n over 2 when n is even. This is obviously not true in general, but we can now determine exactly when it is true. So Jn equal n over 2, which is 2l plus 1 equal, n can be represented as 2 to the power of m plus l. Now that n over 2, so we're going to divide it by 2, and by moving them over to find out L is equal to 1 over 3 times, open bracket, to the power of m minus 2. So we can find the solution to what the L is. If this number L is an integer, then n will be a solution because L will be less than 2 to the power of m. That's exactly right, because we're doing some minus of some number from the 2 to the power of m. So it's not hard to verify that 2 to the power of m minus 2 is a multiple of 3 when m is odd. Well, I have another question is, why is, if 2 to the power of L is less than 2 to the power of m, does it make it a solution to the Josephus problem, right? That's something we can explore more. Maybe someone has the answer to this question, or whoever watching this video. But it's also something to explore for me. And it's not hard to verify that 2 to m minus 2 is a multiple of 3 when m is odd. We'll get to that. We'll study such things in chapter 4. Yeah, so we'll go to there in chapter 4. And therefore, there are infinitely many solutions to the equation Jn equal n over 2, beginning as follows. So one of the discoveries that are made is that when n is in radix representation, for example, this Jn is equal to, we can move the first binary to the leftmost spot and leaving a 0 at the leftmost, so it's going to be the same as J111, And once there's 1 1 1, there's nothing to move over. It's gonna be same when we move this over to the right. So it doesn't really affect the solution as to doesn't change any values, right? It's never gonna change input value, because whenever we move, it's gonna turn out to be the same. So I guess what the author is trying to do is they want to generalize the case where these turn out to be the same, and I think when n is even number, sometimes that the leftover number can be an integer, and that case gonna be where is the case when n is shifted left one spot or right one spot, and it's gonna be the same in binary representation. I think that's what they're trying to prove, or I hope you understand what I was just saying, is that when n is represented as binary, and then shifted to right or left, it's gonna be turn out to be the same as, for example, 1 0 is when shifted to the right, when leftmost spot is shifted, go to the first spot. I mean cyclically go to the right, it's gonna be 1, and cyclically go to the right, it's gonna be 1 again. Again, for the same thing happens with 1 0 1 0. It's gonna be 1 1 shifted to the left, and 1 1 shifted to the right. So same number, whether it's shifted cyclically shifted to the right or left or right, it's gonna turn out to be the same. We're gonna stop at this spot to just to digest what we've been discovering so far. It's a lot to take in, and there are a lot more to prove in the meantime. A lot of interesting things to discover. So we'll stop it here, and let's see what we can find out more